Hello everybody and welcome back to Algebra 2. Today we're going to be talking about 6-2, multiplying and dividing radical expressions. Let's begin. And just like always, let's start off with a little vocab and review. Write T for true and F for false. All mathematical expressions can be written as an equivalent expression with a denominator of 1. Well, that's true. Every single thing that we write, you can always divide by 1, and it's just going to represent the exact same thing. It's going to be equal. The only difference is, well, it's kind of redundant. So that's why you can have x, but that's also the same thing as x divided by 1. Remember, the denominator is the number on bottom, where the numerator is the number on top. And we'll talk a little bit about that one a little bit later. So an expression can have a denominator equal to 0. Well, that's basically the exact same thing as saying we can divide by 0. And that is a big no-no in the math world. You can't divide by 0. It's not possible. It's undefined. The expression above the fraction bar is the numerator, which, like I said before, we have two parts. You have the numerator, and then you have the denominator. This middle portion is going to be considered your fraction bar, so that's absolutely true. The numerator is always on top of the fraction. Multiplying both the numerator and the denominator by the same non-zero number results in the equivalent fraction. Well, in this case, that's true. Essentially, all you're really doing when you want to figure out if these fractions are equivalent anyway is kind of reducing it down to its most simplified form. So if I were to take a fraction like an x over y and then multiply the top and the bottom number by 2, you're essentially multiplying it by 2 over 2, which means that you're really just multiplying it by 1. And if you multiply anything by 1, you're not actually changing the outcome. In this case, we're just changing the way it looks. So 2x divided by 2y is the exact same thing as x over y, or at least it's equivalent. Now, let's circle the numerator and underline the denominator. Just like shown before, the numerator is all the numbers on top. So we have the 5, the negative 5r squared, the r squared plus s squared, and then the denominator is the 6, 16, and that's c minus 16. Great work. And the vocab portion today is going to be combined. Combine means to put things together or to get a total. To combine means to put together or add two like terms to get one term. The like terms negative 2x to the third and 7x to the third can be combined, and you will end up with 5x to the third. Circle the expression that shows the like terms in 3x squared plus 1 plus 4x squared minus 5 combined. Well, essentially, you're just going to, well, like it said, combine like terms. So we have the positive 3x squared and the positive 4x squared, giving you a total of 7x squared. And right then and there, there's only one answer for that. But just to make sure we get a negative 4, we have a positive 1 minus 5, which sure enough would be negative 4. Combining radical expressions using product or multiplying. If the nth root of a and the nth root of b are real numbers, then nth root of a times the nth root of b is going to equal the nth root of a times b. Now notice the n matches the n. If that is not the case, then we can't actually solve this one out. The index values need to be identical in order for you to actually go through multiplying it out. So if we take a look at the very first one, we get the cube root of 4 times the cube root of 6 is going to equal the 4th root of 24. Well, right here, we have the nth root of a times the nth root of b equals the nth root. So notice the index stay the same throughout, even into the combined portion. Therefore, 9 is false. We have the cube root of 36 is equal to the cube root of 4 times the cube root of 9. All the indexes match. 4 times 9 is in fact 36. That's true. We have the 4th root of 3, the 4th root of 8 equals the 4th root of 24. All the indexes match once again, and 3 times 8 is in fact 24. Therefore, that one is also true. Problem 1. Multiplying radical expressions. Can you simplify the product of the radical expression and explain? Well, let's take a look at it. Remember, when we multiply, our indexes need to be the same. So in this case, if we were to circle our indexes, or the small number in the top left corner, we would be circling the 4 and the 5. Since one is 4 and the other one is 5, the indexes are obviously going to be considered different. And since they are different, we cannot actually simplify the product. We can't multiply these out. All right. However, if we look at question 13 and we circle the indexes, we have a 5 and a 5, which means that these are in fact the same. And since they are the same, we absolutely can simplify the product, and we just have to multiply everything out. So all you're going to do is multiply the radicands, or the number inside the radicals, together. So we get a -5 times a -2, which is going to give us the fifth root, because the index stays the same, of +10. Problem 2. Simplifying a radical expression. What is the simplest form of the cube root of 128x to the 7th power? Remember, the cube root of b to the 3rd power is going to equal b. So the index of the cube root of 128x to the 7th power is going to be 3. That is the small number in the top left corner, right above the radical symbol. Can you circle the perfect cube factors? Well, the perfect cube factors that are going to be given will be anything that you see a cube attached to it. So you have the 4 cubed, the x cubed, and the x cubed times x. And since all of these are cubed, we can actually end up taking them out by getting rid of the cubes altogether. So the cube root will eliminate this cube, and this cube, and turn it into a 4 times an x, which is the exact same thing as a 4x squared. And then whatever is not considered cubed, we're going to keep inside the cube root. So we're going to end up seeing the 4x squared times the cube root of that 2x. Now, the one way I like to do it is essentially virtually the exact same way. What I'm going to do is I'm going to take the cube root of that 128x to the 7th power, and I'm going to kind of break it up into two separate spots. I have the cube root of 128, and I have the cube root of that x to the 7th power. And I'm going to kind of simplify it like I used to. But there is a small little change. So I am going to use prime factorization. I am going to go down by just taking out the smallest thing possible each and every time. In this case, the smallest prime number that I'm going to work with for the 128 will be a 2. I'll get 2 and a 64. You then have 2 and a 32, 2 and a 16, 2 and 8, and then finally we have the 2, 4 with the 2 and the 2. Now the difference is, normally with the square root, I say you always pair them up. But in this case, since it's a cubic, our index is 3, I'm actually going to turn them into a group of 3. So I'm going to take out 3 each and every time. And since this has a trio, if you will, of 2's, I get to take out 1, 2. This is another trio of 2's, I get to take out another 2. And sure enough, 2 times 2 will give you 4, which is what we were looking for before. We also have a 2 left over, so we know that inside the cube root, there's going to be a 2. So what I'm going to do next is actually very similar to this. The only difference is we have 7 x's. X raised to the 7th means that we're going to multiply x times x 7 separate times. So instead of me going through the prime factorization tree, I'm just going to write out 7 x's. 1, 2, 3, 4, 5, 6, and then 7. But the thing I'm going to do is, again, the index is 3. So kind of like the prime factorization, I'm going to group these up into trios. So we have a 3 x's right there with the 3 x's right there, which means that I can take out 1 x, I can take out another x, and just like I did over here with multiplying the 2 times 2, I'm going to do x times x, and that's going to give you an x squared. And once again, whatever's left over, we're going to keep inside the cube root of x. So I'm now going to take what's left over number-wise, and I'm going to multiply by what's left over variable-wise together, giving me the cube root of 2x. And sure enough, that is exactly what our answer was. Problem 3. Simplifying a product. What is the simplest form of the square root of 45x to the 5th y to the 3rd times the square root of 35x y to the 4th? Complete the steps to simplify the square root of 45x to the 5th y to the 3rd times the square root of 35x times y to the 4th. Well, the very first thing that we're going to do is, since both the indexes are the same, in other words, they're both technically a 2, it's just an implied 2, right? We can now write them as multiplication on the inside of the square root. So we have the 45x to the fifth y to the third times the 35xy to the fourth. We are now going to multiply the 45 times the 35. And we're also going to multiply the x to the fifth y to the third times the xy to the fourth. Basically, we're going to group up the numbers with the numbers, the variables with the variables. And then we're going to start to simplify things down. Now, what they're saying here is that 45 is the exact same thing as a 9 times a 5. And they're doing it because they know that 9 is going to be 3 squared, and they also see that 35 is going to be a 5 times a 7. And since we also have another pair up of 5, we're going to realize that 5 times 5 is the same thing as 5 squared. But the other side, we're just going to add all the exponents up. So 5 plus 1 gives you the x to the 6th, and that 3 to the plus 4 will give you that y to the 7th power. Now, they're going to, again, bring the 5 and 5 is going to end up being a 5 squared. The 9 is going to give you that 3 squared, because that's what 9 equals. And then we also have the x cubed raised to the second power. If we wanted to write this as a perfect square, we're essentially just going to divide that 6 by 2, and it'll give you 3. So that's why they have x cubed raised to the second power. They did the exact same thing with the y to the 7th power, because we're going to get y to the third raised to the second power. And the reason that they end up having it like this is because that is 6 of our y's, but our final y, that y by itself on the outside, is going to make it 7 total y's. Once we do that, we can take the square root of all the perfect squares, simplifying it down a little bit farther. So the 3 squared became 3, the 5 squared becomes 5, the x cubed squared becomes x cubed, the y cubed squared will become y cubed, and then we still have the square root of the 7 and the y, because we can't take the perfect square of the 7 by itself and the y by itself. So now we have a 3 times 5 times x cubed times y cubed, so that's going to give you a 15 x cubed y cubed with a square root of 7y. Property combining radical expressions quotients. So essentially, instead of doing the multiplication version, we're going to now start dividing. So if the nth root of a and the nth root of b are all real numbers and b doesn't equal 0, then the nth root of a divided by the nth root of b equals the nth root of a divided by b. Virtually, it's the exact same rule. If the indexes match, then they're going to be able to be divided on the inside of the radical each and every time. So which expression is equivalent to the third root, or the cube root of 7, divided by the cube root of 4x squared? Well, anything that says the cube root of 7 divided by 4x squared is going to be correct, making it choice C. Now, what is the simplest form of the square root of 50x to the 6th power divided by the square root of 2x to the 4th power? Well, I'm just going to rewrite this all into one set. So we have a 50x to the 6th power divided by the 2x to the 4th, and we can do that because they are both the square root. They both have the same index attached to the radical. In this case, the absence of an index attached to the radical, and therefore we can start simplifying it down. So we have 50 divided by 2 gives you 25, and you have x to the 6th divided by x to the 4th. Well, remember, when you divide variables, you're just subtracting the exponents. So we have 6 minus 4 giving you the x squared. So we should have a 25x squared on the inside. Now, to simplify it down one step further, we do have to pay attention to what we would get if we actually took the square root of the 25x squared. Now, this is where it's going to be a little bit different. You see, the square root of 25, we all know, is going to be 5. There's no argument against it. It's going to be a positive 5. The weird part happens with the square root of that x squared. Now, remember, you always have a situation where you need to make sure that the x ends up being positive. It needs to end positive because when you square a number like this, it's always going to be positive. However, we can't have a negative x in this case. So our answer is actually going to be the absolute value of, in this case, x. So our answer should be 5 times the absolute value of x, because that x must be positive. Problem 5. Rationalizing the denominator. What is the simplest form of the cube root of 7x divided by the cube root of 5y squared? The radicand in the denominator needs to have a 5 squared and, in this case, a y to make 5y squared a perfect cube. In other words, we are trying our best to make sure that we can get rid of this cube root. Now, the first way that they're going to do is they're just going to start adding things to the bottom, which means that we're eventually going to add things to the top. And in order for us to attach things to the top and the bottom, we're going to actually be multiplying both the numerator and the denominator by what we need for the denominator. In this case, we needed 2 more 5s, that's why they have the 5 squared, and they also needed 1 more y in order for us to get a 5 cubed, y cubed, which is what we're trying to get to. And the reason we're trying to get to that perfect cube is because we have the cube root. All right, so we are going to multiply both the numerator and the denominator by just that, the 5 squared y, to rationalize the denominator. So let's see what this would look like. Well, essentially, we're just going to rewrite everything as we see. We're just going to multiply, like we said, the 5 squared y divided by that cube root of the 5 squared y as well. And when you multiply everything out, since the indexes are the same, we can just multiply the numbers with the numbers and the variables with the variables. So we have a 5 squared times a 7, giving you a 5 times 5 times 7. So 5 times 5 is going to equal 25. And then we multiply that by 7, giving you a total of 175. We then also have the x times the y, which is what we show right here with the xy. Next, we're not going to actually multiply these numbers out. Seeing how we turned them into perfect cubes, there's no sense in actually multiplying them out because we know what it's going to eventually fall back to anyway. So now we are going to get, in this case, 5 cubed because we have 5 squared times 5. And if this was kind of like a variable situation, you're just adding the exponents. So we get 5 to the first power times 5 squared, 1 plus 2 will give you 5 cubed. And with the variables, we have a y squared and a y to the first power technically, again giving you y to the third. 5 cubed, y to the third, or y cubed, are both perfect cubes, which means if we take the cube root of this entire function, we would actually end up with, well, everything's going to stay the same on top, because you can't simplify down that 175xy. However, on bottom, it's going to turn into a 5 times y value. Now, just like we talked about a little bit before in the previous question, since this is a cubic, we don't have to worry about the absolute value. What's positive is positive, what's negative is negative. Whereas if this was a 4th root, we would start worrying about making sure that the y value is absolute or not. In this case, we're going to keep everything on top as the cube root of 175 times xy. And then we're going to bring everything on bottom, we're simplifying it down to a 5 times y. Which brings us up to the last little bit, explain why both the numerator and the denominator are multiplied by the expression. Well, it kind of goes back to that very first slide that we talked about. And that is, if you multiply a number on the top and the bottom of a fraction, essentially you're just going to be multiplying by the value of 1. And when you multiply an expression by 1, the value of the expression does not change. So although it looks different, the actual value is going to stay the exact same. And finally, we made it to the lesson checks. Let's get going through this so we can finish it off nice and quick. All right, divide and simplify the square root of 21x to the 10th divided by the square root of 7x to the 5th. Now, there's going to say that we want to use the rationalization of the denominator as well as combine radical expressions. Then they're going to show the division process using this method right here. So they're going to basically square the square root of 7x to the 5th, but since they're going to do that by the denominator, they are also going to multiply that by the numerator as well, and then they're going to simplify everything down and break it down and do all that wonderful stuff to give you that x squared times the square root of 3x. I'm going to get that same exact answer, only I'm going to realize that we're dividing using the exact same index. So essentially, instead of it being the square root of 21x to the 10th divided by the square root of 7x to the 5th, I'm going to turn mine into the square root of 21x to the 10th divided by 7x to the 5th. And when I do that, I'm going to get the square root of 3x to the 5th. Now the problem is, I still need to figure out the square root of 3x to the 5th. I have to be able to pull out what I need to take out. So in this case, we have the square root of 3. Well, we can't simplify that down, so we're going to keep that on the inside. But this x, I'm going to write 5 times. 1, 2, 3, 4, and 5, because I know that x to the 5th is x times itself 5 separate times, and since we're talking about the square, or the index of 2, I'm going to pair up my x values. And whatever I pair, I'm going to take out. So we have one x that we're taking out, and we have another x that we take out. Multiply what you take out, keep whatever is left over inside the square root, and we're going to be left with the x squared on the outside, which you can see right here, with the square root of 3 times your x on the inside. And that would be how I would go about solving out that problem. Both of which give you the correct answer though. Now the one thing I will say is this: since we did take the square root of something, we ended up getting out an actual variable. The variable needs to be positive. However, x squared will always be positive, so we don't have to worry about writing the absolute values. And the very last lesson check: write the simplest form of the cube root of 32x to the 4th, and then complete to simplify. So looking at this, they're going to try and get the most perfect cubes out of this scenario. So 32 is going to be the same thing as 2 cubed times 2 squared, because 32 is actually equal to 2 to the 5th power, and 2/3 times 2 to the 2nd power, 3 plus 2 will give you the 5. But they also see that we have an x to the 4th, which is going to be written as x to the 3rd times x. And when you end up going through that portion, we're going to get rid of the perfect cubes. So we have a 2 on the outside and the x on the outside, giving you a 2 times x, which is 2x. And then whatever is left over on the inside of the cube root is going to end up being what we couldn't take out beforehand. So that's going to be the 2 squared, or the 4 times your x, which is 4x. Again, I'm probably going to split it up. I'm going to have a 32. I'm going to do the prime factorization, so we get 2 with 16, 2 and 8, 2 and 4, and then finally 2 and 2. And I'm going to, in this case, since it's an index of 3, I'm going to group up into 3s. The only thing that we can, in this case that's 1, 2, hence the 2 on the outside. And I'm going to keep the 2 times 2 on the inside, which is going to be that 4. So we have the 4 on the inside, the 2 on the outside, and then the very last little bit, again, I'm going to rewrite all of the x's, which is all 4 of them, and I'm going to again group up the x's into a group of 3, which means I can take out that 1x, leaving my cube root of x left over, and then that's going to give me my 4 on the inside of the cube root, as well as my x on the inside of the cube root. Well, that is it. I hope everyone has a wonderful day. Stay out of trouble. Don't do anything stupid. And I'll see you guys in the next one.